finally, you will see your supervisor, Dr. Stéphane Cotin, research director in India.
Okay.
So you have 5 minutes.
Oh, yeah. I will share my screen. Could you now see my screen? Okay. So hello. I'm Sergei, and my thesis topic is identification and characterization of boundary conditions for patient-specific biomechanical simulation. And today I'm going to present to you the research and the results of my study. My PhD topic is part of a big project which is called HyperNav project. It includes 13 research institutes and 16 PhD students, and the main goal of this project is to create a surgical navigation platform which helps with surgical workflow. As an example, a liver surgery was taken because it's one of the most common surgery in the world. Each research institute is working on a certain aspect of the problem. In my case, my goal is to specify boundary conditions to improve the simulation accuracy of the liver. Let me first introduce the context of my work. So typically during surgery, surgeons would like to see the positions of tumors and internal liver structures. It will simplify surgical procedure and reduce postoperative complications. However, usually they use cameras that could provide them only with a superficial local view. One possible solution is to use biomechanical model of liver. Registered on intraoperative view, it will predict the behavior of the liver and therefore describe the positions of internal structures. It's important to mark that this prediction has to be done in real time, since during manipulations, surgeons would like instantly see the changes that was done with liver organ. The essential moment here is we work in a patient-specific context. So we have to adapt the parameters of our biomechanical model to work with a specific patient, to simulate the behavior of a specific patient. There are three main components which every biomechanical model contains: its liver shape, its biomechanical parameters, and its boundary conditions. The liver shape could be taken from preoperative CT scans, which surgeons are usually done for planning purposes. In case of biomechanical properties, they could be taken from elastography, particularly ultrasound elastography. There are also a lot of works which describe the biomechanical properties of liver. But in case of boundary conditions, to the best of our knowledge, there is no technique with which we could measure them, and the information about them is generally missing. However, they are important. To show that boundary conditions are important, we decided to perform a simple experiment. We take a brick, which we modeled with hyperelastic material, we fix it from one side, and we apply stretch force. We also add 9 validation points to see how the brick deforms in case of different scenarios. And we modify the stiffness of the material brick and as well as boundary conditions. By modifying boundary conditions, we replace this fixed region by 2 small fixed points at the corners of the beam. The result shows that in case when we change boundary conditions, the difference in deformation could be compared with the case when we increase the stiffness on 100% or decrease it on 33%. And this actually a lot, and it shows that we accurately boundary conditions definitely influence the biomechanical behavior of the object. In case of liver, the boundary conditions are mainly presented by ligaments, which cover liver from different parts. The liver ligaments are not real ligaments by peritoneum folds. A peritoneum is a serous membrane in abdominal area, which covers different organs and structures, including liver. Unfortunately, this peritoneum is studied very poorly, and so the description of ligaments is limited only up to their general information. Apart from ligaments, there are several blood vessels inside liver. They could be detected by a CT scan, but they usually form attachment of the liver to the blood vessels only one particular region. And so they do not completely determine the shape of the organ in case of different deformations. Therefore, as we could see, the information about boundary conditions around liver are limited up to general description. So we need somehow to create approximation to simulate the influence of these boundary conditions on the liver. In case of general surgical operation, there are two data available. First of all, we usually have preoperative CT scan that surgeons take for planning purposes, and also we have intraoperative recordings. These intraoperative recordings are not very accurate, and they usually describe only superficial behavior of the liver, but they could give us some information about the behavior of the liver related to a specific patient. And so we could estimate boundary conditions based on the available data. The problem of estimation of boundary conditions is not new. There are already several approaches that are dedicated to this topic. The first approach is where authors define so-called compliance boundary conditions. The authors introduced the notion of region of interest and guess that this region of interest is attached to the whole object using some additional attachments which they present as aligned springs. These additional attachments they form an influence on the region of interest, and the authors try to estimate them by comparing the constraint and free motions. As a result, they get some estimation for the aligned springs. The main limitation here is that to solve the estimation system, we need to have some observations inside the region of interest, while usually in our case we have superficial observations. And also this approach is sensitive to accuracy of the observations. In the second paper, the authors have two shapes of the same liver, which is acquired in different deformed configurations. They present boundary conditions as certain constraints, and they try to identify them by matching one shape to another. And the transformation matching will give us some information about these boundary conditions. By presenting these constraints as force field, they estimate the parameters of the forces which were applied to perform this transformation. The main limitation here is that this approach requires two complete configuration of the same organ, while usually for diagnosis purposes surgeons take only one CT scan. And the third approach is based on inverse simulation. The authors propose to estimate boundary conditions as forces with unknown intensity. They have a model which simulates the behavior of the object, and also they have some sensors which describe the position of the real object. They express the positions of the sensors in terms of unknown intensity, and then they try to estimate them by minimizing the difference between sensors on the real object and on the simulation model. And as a result, they get the parameters for the intensities. The main limitation here is we implicitly imply that in case of inverse simulation, our model perfectly simulates the behavior of the real object. While in our case, we usually sacrifice the model accuracy in favor to get a real-time performance. The observations in this case also has to be very accurate. Therefore, without finding any idea, we propose our own solution to estimate boundary conditions. Our solution is based on the liver model, which we simulate as hyperelastic material, and ligaments model, which we simulate as springs, which are attached to this liver model. It contains two steps. During first step, we generate initial approximation of our spring positions and parameters. During second step, we correct our initial approximation based on intraoperative images which are available for a specific patient. Let's now look in more details on the underlying model. So on the next slides, I will describe in a bit more details the model which we choose to simulate liver and ligament. A liver is a typical volumetric object. In case of liver, we need to simulate the positions of internal structures and tumors, and therefore we need a model to simulate the internal behavior of the liver. So finite element model is a good choice to do this. Also, we need to stay in real-time context, so our model has to be quite light. And the experiments show that liver model has a non-linear stress-strain behavior. Therefore, there are several possible choices. We need to use hyperelastic model with the simplest materials, like Saint-Venant-Kirchhoff material, Hookian, or Munir-Rivlin. So to select the best option, we decided to compare these materials. We perform all experiments in SAPA framework, which allows us to simulate the behavior of finite element models in real time. Since surgeons usually to access the posterior parts of liver bend the anterior parts, we decided to use bending simulation as a simulation to compare. Also, for our beam model, we use different materials and we compare the simulation results as well as their computation time. The result shows that for all hyperelastic materials, the simulation accuracy is approximately the same. The difference is not more than several percent. On the other hand, in terms of computation time, the fastest is Stenton and Khrushchev material. Neohukian is 6% slower. Community is slightly bit more slower. Therefore, since our main idea is to perform simulation in real time, we decided finally to choose a hyperelastic model, which is based on Stenton and Khrushchev material. The ligaments are thin continuous membranes that attach liver to the surrounding organs and tissues. So to simulate the ligaments, we need to look at the theory of thin plate elements. There are several possible choices. We can use a general finite element model and use just a thin model. We could use superficial models like constant plane triangle or shell elements, and also we could use masking system. The masking system is a more appropriate approach for us, since it's fast and it allows to easily handle topological changes. And finally, our main idea is not to simulate the ligaments accurately, but only to simulate their influence on the liver model. Therefore, we decided to use a mass spring system to simulate the ligaments behavior. Talking about ligament stress strain curves, the ligaments are, unfortunately, there is no information which is dedicated to description of human peritoneum, to stress strain relation of human peritoneum. So we decided to look at stress strain curves of general human ligaments, including ankle and knee ligaments. The description in general, the stress strain curve is split into three parts. There is a polynomial part on the first part is polynomial part where the fibers are unfeatured. The second part is linear region where we stretch the fibers, and finally we have a fracture. Anyway, in most researches, the ligaments are simulated with nonlinear models, so we can't rely on linear springs, and therefore we decided to rely on cubic springs to simulate the ligaments behavior. In case of cubic springs, the reaction force for the spring contains two parts. The value of the force, and we simulate it as cubic polynomial curve based on strain, and the direction of the force, and we simulate it as the direction of the force in case of linear spring. To verify how our model works, we compare it with a referent hyperelastic model. To perform this comparison, we selected all stress strain curves related to description of all ligaments from several papers. Then we selected minimal and maximal curve from this set of curves. Then we generated a shape which presents a piece of thin continuous membrane, and we simulate this shape with hyperelastic Neohukian material. And finally, we find the parameter, the Young's modulus, with this Neohukian material, the way that it behaves like the described stress strain curves. After that, we generate a mass spring system which has the same shape, and then we estimate the parameters of mass spring system the way that it behaves like the hyperelastic material, and we compare the results. Since we are interested not in simulation of ligaments, but only on their influence on the liver model, we compare only the attachments to the liver, which are marked as yellow spheres. And the result shows that with these attachments, for strains up to 45%, the average difference doesn't exceed 3 millimeters for both curves. And since all other curves lie in between this maximal and minimal curve, we expect that the difference for other stress strain relations remains the same. On the other hand, the mass spring system is approximately 30 times faster than finite element model. And therefore, to simulate the ligaments behavior, we decided to use a cubic mastering system. Let's now look at the components of our approximation, of our estimation process. In case of lever positions, we decided to rely on statistical atlas. We don't know, unfortunately, the positions for a specific patient, but there is data available where the ligaments are segmented on the lever model. And we could use this data to construct statistical atlas, which is a common approach in the medical domain, and then use it to approximate the positions of our ligaments. The essential moment here is that every lever shape is patient specific, and there is no the correspondence between them. So to solve this problem, we rely on large deformation diffeomorphic metering approach. In this case, the main idea of this approach is to perform deformation as a shape transformation, which is based on a certain amount of interpolation parameters. To compare the shapes, we use a varifold metric, which is meshless. And based on this varifold comparison, we could define registration as substitute finding the metering parameters the way that the transformed shape will be similar to target shape in terms of varifold component. And the average shape, to compute the average shape, we could take one shape from the database, we could elastically register it on all database shapes, and then compute patient mean, which minimizes the registration variance. Using a registration and average shape creation approach, we finally construct our statistical atlas. So initially we have a set of levers with segmented ligaments, and we align them. Then we construct an average shape. We compute statistics on an average shape to avoid any shape variations related to a specific patient. Then we register all elastically register all shapes on the average shape, and then extract a set of curves which are related to segmented ligaments. For these segmented ligaments, we then compute statistics. To compute statistics, we intersect the shape with a set of planes, and we compute statistics in every plane. The intersection of planes with the curves gives us the points, and for them it's easy to compute statistics. And we compute average and standard deviation. The configuration of set of planes depends on type of ligament, but we use we generally use parallel planes and radial planes. Then we match our statistics with shape interpolation functions to the average shape, and we register our average shape on the target model using elastic registration, and we apply these interpolation functions to extract the statistics for the target shape. And as approximation of our ligament positions, we use a statistical average. So for elastic registration and average mesh creation, we use Deformetrica software, which is freely available for non-commercial purposes. To verify how our approach works, we decided to perform experiment. We take 15 lever models with segmented ligaments. We use 14 meshes to generate statistical atlas and one mesh for validation. On the slide, you can see the the result of distribution of segmented curves, which are registered on the average shape. On the next slide, you could see the result of the statistical atlas registered on the validation mesh. It's visible that the statistical average, which marks is with yellow dots, differs from the curves that were segmented manually, which mark with the black dots. The difference is different for every ligament. For falciform ligament, it's approximately 2 centimeters. For coronary, it's 6.5 millimeters. But according to our knowledge, this is the best approach to approximate the positions of the ligaments, and also we expect to compensate for this for position difference by estimating slightly different parameters during our correction step. Let's now look at initialization of ligament parameters. Since we don't, unfortunately, there are no available constitutive laws related to human peritoneum, but we finally find a paper which describes the stress-strain curve related to pig peritoneum, and we use this stress-strain curve to initialize the ligament parameters. Our initialization process contains two steps. Initially, we generate a hyperelastic model which is described with the shape of a piece of thin continuous membrane. And we perform model stretching, and we substitute the parameters. We use Miyahookian material, and we substitute the Young's modulus for this Miyahookian material the way that it behaves like a stress-strain curve. For this, we use FEBio optimization model, which is available in FEBio software. During the second step, we generate the mass spring system, which has the similar shape. We perform stretching of the springs, and we estimate the parameters of the springs the way that they behave similar to the reference hyperelastic model. For this, this estimation technique, we use a filtering approach, which will be described later. And as a result of our parameters, as an approximation of our boundary conditions model, we use the parameters which were estimated for the mass spring system. Let's the correction process. So in case of correction step, we correct the parameters of our boundary conditions model based on intraoperative data related to a specific patient. It's important to mark that in this case, the estimated parameters will be also patient-specific. There are several requirements for this correction process. It has to be in real time, since we perform this estimation during surgery. It has to deal with pathological changes. It has to sequentially process the new observations, since when the surgery goes, we have new observations. And finally, it has to be robust with the observation noise, since our intraoperative tools are quite noisy. There exist several approaches to process this, and finally we decided to choose a Kalman filtering approach. A Kalman filtering approach is relatively fast. It allows us to deal with uncertainty, and finally it allows us to process our data in a sequential manner, and to provide us with intermediate results. So we consequentially update our model as far as new observations are available. In Kalman filtering process, we would have some dynamic process that goes during certain period of time, and we have some observations, noisy observations, that give us some information about this process. We also have some model which simulates this process. It might be imperfect, and we have some unknown state which we are trying to estimate. Initially, we have some initial approximation related to our unknown state. The Kalman filtering itself is a loop that contains two steps. During prediction step, we predict the next state of our model based on currently available unknown state, currently estimated unknown state. During correction step, we compare the predicted observations with the real one, and we update our unknown state based on this comparison. And we repeat this process continuously with getting also intermediate results. There are three main components which Kalman filtering process contains. First of all, it's underlying model. In our case, the underlying model contains of liver model, which we simulate as hyperelastic finite element model, and the shape of the model we take from CT images taken from preoperative CT images. It's also ligament model. In case of ligament model, we simulate them as cubic mass spring system. The positions for cubic mass spring system we take from statistical atlas, and their parameters from available stress-strain curve. The second element are observations. The observations might be some detected features or markers on our liver model. The most important moment that they follow the liver deformation, and they thus give us some description about its behavior. And finally, it's unknown state. In case of unknown state, we take the liver positions and also the parameters of boundary conditions model. Because we're trying to estimate boundary conditions on the other hand, on the other hand, we're trying to predict, we're trying to create the model which predict the behavior of the liver in case when observations are missing. The Kalman filtering process is a stochastic process, and every unknown is presented there as a Gaussian distribution, which has a certain mean and variance. Since for our underlying model we use a nonlinear model, we have to transfer this Gaussian distribution through our nonlinear process. For this case, we use uncertainty Kalman filtering approach, where this transformation is based on transformation of uncertainty. In this case, for Gaussian distribution, we generate a set of sigma points which present the probabilistic information related to our unknown state. We transfer them through our nonlinear system, and we reconstruct the Gaussian distribution based on the transferred sigma points. It's important to mark that we need to have to keep information about mean and variance for all unknowns in our system. So, in case of n unknowns in our system, we need to generate at least n+1 sigma points. The general algorithm looks like this. Initially, we have some initial approximation for our boundary conditions model. Then, at every iteration, we generate some sigma points. Each sigma point contains the parameters of our mastering system as well as positions of ligaments, and some of them are perturbed. Then, every sigma point, we execute simulation step to simulate the behavior of the liver related to next time frame. And we compute the predicted state as mean of all sigma points. Then for every sigma points, we generate predicted observations, and we compute the predicted our final predicted observation as mean for all these observations. Then we get our real observations from intraoperative data. We compare all these observations, and finally we update our unknown state based on this comparison. And we repeat this process continuously. So the main problem in this process workflow is prediction step. Since we need to generate a lot of sigma points, and for every sigma point we need to compute a simulation. Therefore, if our model contains at least several hundred of nodes, we need to generate several hundreds of sigma points, and therefore one iteration of data assimilation process will be very time consuming. So there exist certain possibilities to improve this process. One of them is reduced order uncertainty Kalman filter. The main idea is to perform a state covariance of our model and to mobilize the state in the factorized form. An option will be to use the components which contains the most variance of the system. So, and in our case, we could consider the model stiffness and boundary conditions as such components. Since the covariance between the model positions, in case of biomechanical model, it depends on the stiffness and boundary conditions parameters. The modified approach now looks like this. We have our reduced state, and we generate sigma points related to reduced state. We generate sigma points, generate sigma points related to general state. We process them through our nonlinear system, as in general uncertainty Kalman filtering approach, and then, based on the transferred sigma points, we update our transformation matrix between general and reduced state. And then we update the reduced state of our system. Another possibility is to use preconditioning. A preconditioner is an operator that transforms our space to much more regular space. So if we use an iterative solver to solve our system, it could converge just in few iterations, and finally the simulation step will be faster. The important moment is that the conditioner doesn't have to be the inverse to our system, but it has to be the multiplication by system matrix has to be close to unit. And so the idea that we have in mind is to compute preconditioner as inverse system matrix for one of the sigma points and use them to compute the inverse of our system for one of the sigma points and use it as a preconditioner for all other sigma points during our estimation step. Therefore, since all sigma points they just differ by just perturbing some boundary conditions parameters and model positions, it has to work in general. The simulation process has to be faster. To verify how it works, we decided to perform an experiment. We take a cylinder, we fix it from one side and apply several springs, the parameters of which we're trying to estimate, from another side. We apply also periodic force to perform deformations for the cylinder, and then we apply several positions, black points that serve us as non-observations. And we compare the computation time as well as simulation accuracy for the estimated spring parameters for every version of the filter. The result shows that the most accurate filter is unsorted Kalman filter, but reduced order version just increase the simulation accuracy is 10% less, and in case of when we use the preconditioner idea, it's 16% less. On the other hand, if we talk about computation time, the reduced order version of Kalman filter is approximately 200 times faster than the general unsorted Kalman filter. And when we use preconditioner, it still gives us a 30% improvement. So since we still have to be in real-time context, and since our prediction step is very computationally costly, we finally decided to use reduced order Kalman filter with the conditioning approach. In the last part of this of the correction step, I would like to show the experiment which is related to human liver. We take a patient with the model for the liver was taken from a patient with segmented ligament. To generate ground truth model, we use a very dense mesh, approximately 73,000 elements. We used Ogden material, the parameters of which were taken from the literature, and we use neo-Hookean material to simulate the behavior of the ligament. We also apply periodic forces, and we generate 14 surface markers on the front part of the liver, which serve us as non-observations. To perform a data assimilation step, we use another model, which was approximately 7,500 elements with Saint-Venant-Kirchhoff material. And also to simulate ligaments, we use springs, which were attached to liver and to some fixed points in space. And during our data assimilation process, we estimate the parameters of the springs. For validation, we generate 12 internal markers that were more or less uniformly distributed inside the liver model. And we compare their positions with respect to ground truth data. For comparison, we take two cases. In one case, we simulate the ligament as our mass spring system with estimated parameters. As for another case, we simulate the ligament as fixed boundary conditions, using fixed boundary conditions. And the result shows that simulation accuracy for the case when we use estimated boundary conditions is 3 times more accurate. The difference is 3 times less. And that actually, from this result, we could conclude that if we estimate boundary conditions, it will sufficiently improve the simulation accuracy of the model. As the last step of my presentation, I would like to show you the experiment which was based on a real human liver. In this case, we take a human cadaver, so we simulate an open surgery case. We use 14 surface markers as known observations, which we track, and we use 9 deep fiducials, which were inserted inside liver for validation purposes. During our procedure, we acquired several CT scans. Some of them were acquired for the deformed liver to compare the deformation difference. To manipulate liver, we use general surgical tools, but the markers were recorded with RGBD camera. An RGBD camera is a special type of camera, which in addition to RGB model have one infrared emitter and 2 infrared sensors, which allows us to reconstruct the information related to the depth information related to the whole part of the observable domain. The general process for flow looks like this. Initially, from CT images, we reconstruct the lever shape, as well as the positions of superficial and volumetric markers, and we generate our finite element model. Then we register our statistical atlas on our generated shape. From registered statistical atlas, we generate our masking system. The generated model that was registered on the intraoperative data. And finally, on intraoperative data, we perform data assimilation process and estimate the ligament parameters or estimate the boundary conditions parameters for the masking system. And finally, we perform validation and compare the results. The statistical atlas was created from 15 lever models with segmented ligaments. And as initial approximation for our ligaments, we take a statistical average. Based on that statistical average, we selected a set of points, we extrude them along normals, and then we fix the extrusion. And we also generate masking system to generate the model of our boundary conditions. The result of statistical atlas registration and boundary conditions model creation is presented on the screen. To register data on the intraoperative images, we selected superficial surface markers, which we extract from CT scan and also from RGBD data. And then we use iterative closest point approach to match these surface points. Then for stochastic estimation, we segment markers on to perform stochastic estimation. We segment markers on the RGB image. And with this segmentation, using depth image available, we reconstruct a 3D position of point cloud. Then to generate trackings for every observed marker, we match the point clouds on the neighbor frames based on minimal distance approach. And finally, we use these trackings for data assimilation process. We selected several of them as control points that control our simulation, and others as observation to perform data simulation approach. To see the results, we use 9 deep fiducials, which we inserted inside the lever model, and then we take 2 CT scans, which were acquired for the lever, registered in different shapes. And since we observe surface part of the lever, we guess that we track the superficial part perfectly, and so we match the superficial points for both CT scans, and then we compare the positions of deep fiducials. For comparison, we selected 3 scenarios. In first scenario, only blood vessels were simulated as a fixed region. In second scenario, we added also masking system, the parameters for which were taken from statistical atlas and stress strain curve. And in third scenario, we use a spring system with estimated parameters. The result shows that in second scenario and then in third scenario, there is certain improvement, but still the improvement is much less than for the case when we use synthetic data. There might be different reasons for this. One reason is we take into account only falciform and coronary ligaments, while there are still hepatogastric and hepatoduodenal ligaments, which actually are close to the deep fiducials 5 and 6, and which has the most difference. Then also we don't take into account contacts, which happens with the liver when it contacts with surrounding organs and tissues. And finally, instead of simulating the impact from surgical tools, we use several points, observed points, as control points, and they are also noisy. So as future steps, we propose to focus on the given problems and try to find the solutions for them. It would be also nice to implement the data assimilation process on GPU, since for now it's implemented on CPU and it's close to real time, but still not real time. And we hope with the GPU it finally becomes real time. And finally, in case of RGBD camera, instead of tracking several markers, we could reconstruct the point cloud related to the whole visible part of the liver and then use this reconstructed point cloud as our observations to estimate the parameters of boundary conditions. It's also important to mark certain limitations of our approach. In case of statistical atlas, our elastic registration depends on initial alignment and works only with accurate segmentations. Also, when we intersect our model with planes, it is valid only when we compute statistics for curves. In case of correction step, we need to somehow to find the statistical parameters to initialize our state model variance. Also, Kalman filters works only with Gaussian distributions, while in general case, some other distributions might describe the stiffness parameters better. And finally, convergence rate depends on initial gears. But despite all limitations, we still believe that this approach is the best approach to estimate boundary conditions for the lever model with respect to the known data. As a conclusion, I would like to say that the main purpose of this work was to improve the simulation accuracy of the lever model by taking into account the influence that are made by boundary conditions. In case of lever, they are mainly presented by ligaments, and information about them is generally missing. So the idea is to initialize them based, first of all, on statistical atlas and available stress strain curves, and finally to correct them based on intraoperative data. And the result shows that there is a certain improvement in simulation accuracy when we estimate boundary conditions. During my PhD studies, I participated in several publications. I also participated in several conferences, and I do all my PhD courses. Among other achievements, it would be nice to mention the Optimus plugin. It's a part of SAFAR framework, which allows us to estimate different parameters using nonlinear Kalman filtering process. And then I would like to thank everyone who helps me with thesis writing, with my mid-thesis thesis and thesis defense, and also with real data acquisition and real data processing, and finally with software. Thank you. Yeah, maybe you have to be closer to this microphone because. No. You can.
Now?
Yeah.
Yes. First, let's thank the nice presentation platform, the very which helped us to understand the now to the next question. And first,
thank you, Nadia. So, Sergei, first of all, I wanted to thank you for this great presentation that is strengthening your work and strengthening your thesis. I read it. To be completely frank with you, it was exciting me to read such subject and also fearing me because usually I used to read any thesis, so I was fearing to be the stupid guy reviewing it. I really enjoyed your thesis and I really enjoyed your presentation. So for all of these, I do thank you.
Thank you.
You are currently studying one of the most challenging topics in universal estimation applied to biomedical treatment. and you're combining, I think, most of the difficulties. First of all, you want to work in real time, which is, I think, a fail, in the sense that it forces you to reduce as much as possible your the complexity of your models, and sometimes reducing the complexity of your models leads you to make some choices that might be challenging. And you are also studying some very complex problems that are related to non-linear behavior, large transformation, unknown boundary conditions related to the ligands. The ligands are quantity or irreducibility of medical images. So combining all of that constitutes one of the most difficult things, but it also corresponds to the name of nothing is really known from the scientific on the. So you may know I'm working on different organs, but finally our question and our the PhD was part of the. So we are very close from the scientific and questioning viewpoint. I do apologize, I will have thousands of questions that So I would like, if you agree, I would like to focus rather on those two elements that you introduced in your presentation and that are in your manuscript and that question. The first one is related to the choices of elements you make for the ligands. So indeed, I agree with you, the ligands you have on real ligands, there are fascias with densification, local densification, which leads us to think they are ligands, but they're not really. But that raised me, that really raised the question from we decided to model them with springs while we membrane. And specifically for one of them, so the falciform ligament, as far as I remember, the falciform ligament is one that goes in the depth of your liver. So I was wondering if you tried something thinking for a short period about real time, if you try to compare the numerical simulation modeling includes ligaments with cells, with other elements, and compare these simulations that you try to make some conceptual analysis of the bias that you're introducing there?
Oh, yeah, that's a good question. So what I could say is that we decided to focus on mapping system mainly, yeah, because of real-time, not only because of real-time context, but also because we want to simulate only not the ligaments themselves, but only their influence. If
when you try to, I agree with you. That's also raising the question when you were in your manuscript, when you were justifying the reason why you were as far as I remember, when you were explaining and the numerical simulation you were completing were only a simulation where you were applying only one of the two. And my question was, did you try to compare the simulation when you were applying both types of loads, and what might be the consequence and the difference between shell
Ah, Yeah, if I understand correctly, you are asking about me the stretching of the reference model and the mass spring model, and instead of applying forces, you would like to apply the displacements.
Using both is that you will or you will not play.
No, talking now, I haven't tried to compare them in case of when we, instead of using forces, we're trying to use displacements, and there will be a certain. Okay.
I had also one question. I think it's on your slide 8. You are your model to here. So that's the here. You are trying to analyze the benefits of your free approach. But you are telling us that your average difference in terms of the measure is less than 3. But what represents 3 millimeters with respect to the observed displacement in the ground? Is it neglectable? 3 millimeters neglectable with respect to the magnitude of the displacement that you are observing and or simulating, or do they have the same
No, as for us, we're trying to find a model which is quite fast and still has is very close to is quite accurate. And we use this Neo-Hookean reference model as a ground truth model, since we don't have any information about real data.
Yeah, I agree with that. The fact that you are comparing on that slide, you're comparing the CPM with
Yeah.
some and if you go back level at 500 megapascal, the difference is less than 3 millimeters.
Yeah.
These difference of difference. Is it important with respect to what you are relating
in general, well, it's small. It's maybe not so small because in general we say that the difference less than 5 millimeters is okay. But of course, it's not only the difference that we introduced by replacing this model. There are also a lot of other inaccuracies. When we use Sentinel-Kirchhoff model material for lever, when we estimate parameters for all boundary conditions, and of course we don't estimate the ground truth parameters, it's only approximation. So if okay.
You mentioned earlier, you were mentioning that some constitutive model were leading to larger time of computation. So if I remember well, I think that the Newton was the most interesting. It's nothing too obvious to me why time of computation is increasing with respect to the
Yeah, actually for comparison we use Safan, which is all our group is actively working, and I perform all this comparison in Safan software. And the implementation, how model were implemented in Safari, it might be different from the implementation of them in another software. So apart from the theoretical description, they are different theoretically. It might be also that they are a bit differently implemented in softwares. And finally, when I compute estimate the computation time, I estimate the computation time in this SAFA framework.
Do you have an idea of the reason why they are using such different kind of computation? Because both are, as far as I remember, both are depending on only on one thing target, on the computational time. I think the rate is to be as easy to calculate, so I really don't understand, and that's a SOPA question, I really do. But do you have an idea about the reason why there is such difference in SOPA?
Well, one reason for this might be is in SOFA it's like like I presented on my slides. It's usually a lot of sacrifice in favor to get a real-time performance, and there might be certain optimizations that are implemented in these hyperelastic materials, which leads to this, or which were implemented for Sentinel-Kirchhoff material, and then for Hooken, which leads to such big difference in the computation time. But, well, I could say that sometimes they are not very accurate in favor to get the simulation SAFA is not very accurate in favor to get a real-time performance.
Yes, so that means that
In general, yes.
That even when you were comparing the accuracy of the different model approaches, you were still focused on the real-time approach, meaning that you were getting not completely converge on the energy. That's right.
Yeah. Oh, well, if we use another software and compare the models in another software, it might be also will be some difference. But for now, software is the only software which I guess not only me, which we know, which allows us to do something in real time. And we mainly working with SAFA because of this. So.
And we force SOPA converge on energy getting rid of real time.
I guess the answer is yes. Maybe not changing some parameters, but just implementing some code.
One thing surprised me a lot in your PhD, I do trust you because you repeated it during your research. So there is really no experimental data about the mechanical behavior of the liver.
Of the ligaments, not of the liver. Human peritoneum. And actually, there is a paper of White, which from where I took a description of peritoneum of pig. And the authors, they say that according to their knowledge, the first paper where they described the test and curves related to peritoneum. And also the paper about the general description of peritoneum. I don't forget the authors. They also tell that for many years the human just don't consider peritoneum as a separate tissue, but just as a combination of some other tissues. And only recently they start looking at this peritoneum as a separate tissue and start looking at their behavior. And they also give a description of peritoneum, and this description just describes only general the proteins, the amino acids, and some other components which plutonium contains, but no information about biomechanical properties at all.
One quick question, but very short one. On this slide, the 26 well, the two were using the antibiotics. Why did you use antibiotics instead of giving it? Is it a choice or just because you didn't know?
Analytically, no, I just find a nice optimization model in FIBio when you just put the points related to space and curve, and it computes by applying the curve fitting approach the parameters of your hyperelastic model.
Do you use FIBio to measure something, or is it automatically just on the curve?
Yeah, I need to select points and then to put them in the configuration file, and then the FIBio computes.
Without making the sample that fits the protein.
Yes.
That's an addition. My last question, but I think it's probably one of the most important to validate keywords relates to the atlas that you were considering. Who created your ground truth information? Is it one single fishery that identifies your ligaments, or is it several ones? And if it's the same, to be completed that only? So there is a bunch of questions that your statistical data. So who completed that?
Nicholas Gols, he is Nicholas Gols, and yeah, it's only one specialist, and he segmented them manually based on his expertise. And yeah, I know that this is very deviated data, but unfortunately for now is the only data that we have. And still these statistics give us some information about initial approximation of ligament positions. While without them, it's much harder to understand where they are.
Yes, I do agree. And do you know what could be the influence of increasing or reducing your basis? Did you try, or is there any information in the literature that helps you have a better idea of what's the minimal size of your initial space or your initial atlas in order to make sure that you will have something accurate for the approximation of the different models? Is there some literature about this on the number of atlets?
You mean a number of models which we could use for statistics? I don't think so. I guess the more the better.
Yeah, but did you know, and you mentioned that it's really hard to finish the data. The question is also how much are required to try to finish the outcome.
Yeah.
So as far as I remember, I think that's what you mentioned during your presentation, you use 10 to build your atlas and to compare with one only.
Yeah, I use 14 to build atlas because we have only 15, so yeah, I use 14 to build atlas and 1 to compare. And
just using 10 and try to reach 5, or to use well, let's play with the number of initial information.
No, not yet. Well, I found this approach to work with statistics quite recently, and so for now I just only use it to approximate the initial positions of ligaments. While of course I agree that it would be nice to not to use only one mesh for validation, but also to use several other meshes and to look at yeah how the difference, what will be the difference for different validation meshes, and how it depends on the amount of models that we use for statistics. And actually I could say that for now I use Deformetrica software to compute this statistical atlas, and I use sort of deterministic atlas, and there are also another approaches that are available, but for now I use the simplest one just to compute statistics. So at some moment I also would like to look at those approaches, more difficult approaches, but unfortunately I didn't have time to do this. It would be also nice to look at them and to see will they improve the statistics accuracy, or will they change something.
Nadia, do I have time for one very last question?
Yes, of course. With a very early.
No, 7 is not that early, though. So one last question. Okay, let's. And it's a selfish question, because it's a question that interests me in my case. So please apologize my career. So.
Oh, well, it's okay. I will try to answer.
Just guess, or just imagine that you're working on soft organs, such as liver, maybe softer than the liver, but never mind. So soft organs under large strain, very large strain. You have your atlas, and your atlas gives you only the geometry, the 3D geometry of the organ, with the ligaments on your atlas. But now the ground for the data that you have to complete your customization and your identification, the data that you have are only displacement fields in one slide, because we are using some MRI and we don't have some external observers. So you have your 3D model with your atlas, and the data that you have to run your Sandman filter, your correction, and all your numerical tools, the only data that you have are displacement field on one slide. So which other, is it sufficient, or do you need some other info?
And these slides, it's in 3D space. We just well, of course, the general answer will be we have to verify how it works, because the problem of the observability, it's a very difficult problem. Well, anyway, the filter will return. The filter is based on stochastic approach, and so it always returns some results. But the results should be treated as like we don't know the answer, we never know the answer. But this is the more probabilistic result which we have. And so we just need to apply the filter and to see the result that we have, and see if it's something which is close to what we expect, or it's completely different.
What happens is, instead of two, you have 5 pairs. Pairs being non-dimensional.
Well, in this case, what I could say is that the filter is just a least square minimizator. So it just estimates the parameters the way that the observations that we have from liver will be close to the real observations that we have. It doesn't matter how much unknowns we have. Well, it matters. It matters, of course. The more unknowns we have, the more some of them will be completely senseless. But we could think about filtering approach as a least square minimizator, and so we could estimate some parameters. Well, the filter estimates some parameters based on this comparison of these observations. But well, what I could say that it doesn't know what is in the underlying model, so the parameters, the estimated parameters, might be completely unphysical, well, just completely senseless. Just if we have some crazy parameters for which our model, the observations on our model behaves like real observations, and the filter converges to these parameters, it will say that, yeah, these parameters are correct and everything is correct. We don't know to perform estimation anymore. Well, I'm not sure if it answers your question. Well, in this, the idea that I always have in mind is we need just to verify how it works, to see if it gives us something.
That's the key for every people working in the biotech.
Well, one idea that was a book about data assimilation is called twin experiment. So we generate some ground truth data, and we use for data estimation the same model, and we see how it works on this twin experiment. Then, if it works on this twin experiment, we instead of ground truth data, we use another model, more complex, real data, and see is it the same behavior or is the behavior is completely different. And if the behavior is completely different, we need to change something, maybe to estimate some other parameters. Well, for now, this is the only advice that I know, and
that's really, just to conclude, that's really interesting, because indeed I think we are the best discussion I have. I think we are coming from different approaches. We are converting to the same thing. You are proposing to create simple models that will lead to accurate simulation. And I was usually thinking about creating very complex models, taking into account as much information as I could to generate some accurate simulation. But finally, you realize that you may need to complexify your model, and I realize that I will need to simplify my model. It's probably really complex. So thanks a lot for your work, for our discussion. That was really I was really enjoying to read your CV, even if it was during the summer, and even if that was a great thing to do during the summer. That was my book of the summer, and I really enjoyed it. So I do thank you for that. Thank you for your work, and I wish you the best, and hope to see you very soon. Thanks a lot.
Thank you.
Absolutely, no. Of course, I would like to thank the great pleasure which even if the guy who's not doing it, I find a lot of I want to say something I was really surprised when I read your statement. Take a look at the result. I didn't see it that good activity. It's of university. There are less and less things about you make new activity. And I want to company with
Thank you.
literature survey. Next, that's each time you propose something, every question also, but you are certainly at some questions 2.1. And they start when you find if you get some stuff file, when like say because our lab we are working with company which is Amazon is working with and we try to find demonstration right? And we didn't catch very efficient result and we tried very simple elements sensor. And we didn't find some elements to use in extension just have the real equation. That's easy. One element. And then very big stepwise in element. But do not describe the equation. That's too strange. And the postdoc had to come back to the software and come back to the real. Do you look at for default to verify that your equations were perfectly right? Did you notice some progress? Events to the equation? Was very deep and
Are you talking about general simulation or stochastic? Yes. The people are laughing here and
very careful. What were your main preoccupations? You just
sorry, could you repeat your question?
uh,
Because yeah, sometimes there are problems with simulation. And
software or something that is not too much.
Yeah, we could try to fix it in different ways. There's some people just write their own components where they try, for example, John Nicole, he wrote his own component, and where he created his own finite elements, which is a bit different, implemented a bit differently, and they behave more correctly. Sometimes people just try to deal with this to use another constitutive law to try to find a workaround.
I think that you do the thing of develop the point for this problem.
Sorry?
If I touch the use element which will
Yes, yes.
didn't use what you find in the public library, but that's then you can consider that all your simulations are perfectly
In my case, I usually use I use all them together in general. I just look at different finite element models that were implemented and different solvers, iterative solvers, and then I try to compare them in terms of accuracy. Sometimes one method or one solver gives some weird results, I don't use them anymore, just mark them as a suspicious solver or suspicious finite element method and try to use another one. But I haven't verified if all the hyperelastic materials in so far will behave according to the specific curve that we have in literature. It would be of course nice to do this comparison.
what I conclude. The complete question is if to differ
Degree 2 okay.
Second technical question, point testing the scientific point of view. I some words. I have a soft tissue problem. And what about this? The possibility is easiest way to treat the soft tissue. You don't have to ask yourself what is the question ratio, something particular question ratio to model it. The problem is after when you try to perform data, program and the text. So I have what is the question ratio, I can find or 9 or 2 or 3 or sometimes like 2 with 0.48. That is configuration. And I know what is there. Correct. Sometimes it's better which we can play to make the conversion. But the problem has different problem. We can have place can be changed for 30 or 50% local component. You can have the information that's changeable. And when you do your simulation, information that's only do you notice anything that changes your display? That's your question. You notice that information. If you change this convertibility parameter.
Actually, Yes, I could say that yes, and when you see when instead of 0.49 I use 0.48, that usually means that I tried with a Poisson ratio equal to 0.49 and I have some weight behavior. So of course, in general case, we need to implement somehow some stuff to do to implement incompressibility, but as a quick solution, which I have in mind, is just to reduce a bit Poisson ratio and to make the object have the normal behavior. It's of course, yeah, not very accurate in terms of simulation of the real object, but for now, for that time, I just took it as the best solution that I have. So yeah, my solutions yeah, like other people use 0.49, 0.48, 0 a bit less than 0.47. If there,
You know, my problem with it, what I do not like is to say it's incompressible and in reality. So, there is a lot of change. The compressibility, the main problem is that you have full paper, it is, where it says all soft tissue are incompressible. So nobody has to.
but I usually say that it was almost incompressible, but but not incompressible. And finally, what I have to say that another PhD student from Hypernav, he did experiments with the liver, and he finally the results of this experiment was that when he deformed liver, finally it changes its volume. He guesses because of the blood vessel system. When we deform the liver, the blood flows a bit different, and then because of that, the shape of the liver compresses a bit. So it's not completely incompressible model.
That's the main question that is done somewhere. But it just we now it's something that is I think very important that can give many support.
Yeah. Yeah.
I wanted to come back on the material side. 18
Oh.
to a little more your criteria, which is 20 millimeters, and that's the global remark that I had on your PhD. I am a guy who mechanics. And we reduce the material to some point and we look at how points are moving. My question always was, what about your work? Because on your figure, the point that are most important are the one where you have the boundary condition at the top.
Yep.
I perfectly agree. And it's here where you have the most response, and if you will verify here, it is better, no problem. But after, when you go to the liver, complete problem. Are you sure that is a good point? Or can you have something different between point that is true? Can you answer that better involved? Cannot have something more different?
Wait, well, we selected these points since it's the points where the ligament is attached to the liver, and we compare them as the positions, the relative positions of the liver. So we say that with masculine system, the relative position of the liver will be not bigger than 3 millimeters. And we apply the same force for the both models. So the reaction force has to be always the same. And the deformation reaction from the liver side has to be also the same.
When you open a guy that is liver and of PhD, with the complex program, and two what just have a bigger movement and the question that I will answer. I'm not sure that this point only one. That's why I must say I would like to come back to the general geometry. That is the different mechanician. I need to see what are made because sometimes can have surprise on more simple problems, but we are speaking in the lab where we were using needles. We were looking for the needle. You say, hey, very good at somewhere. The needle is forming. You can have those work really fast because you have 3 points to measure, and 2 points to the two matter. So one big problem. Here with a very, very point that you manage very well. But I'm wondering if you are able to come back to the team to think that your method is the best thing. That was my main consideration. I don't know if you catch what I wanted to say, but
yeah, I'm not sure.
When you present the full financial of the wood deformation and here as you have just a measure number, it's difficult to your error is 3 meters everywhere, 3 meters length. If 3 millimeters is the maximum average, but somewhere length, main interrogation.
Well, it's not 3 millimeters everywhere, and the yellow spheres shows this because in I couldn't show. Well, I could maybe show with my mouse. Yeah, here for this yellow sphere and for this yellow sphere, the difference is definitely more than 3 millimeters because, as you see, these yellow spheres they are more. They have a different curve, and while this one have also different curve. For other points, it's less than 3 millimeters.
On this simulation, which is very good simulation, when we are going to the liver, different. If you are nothing to verify error, I'm sure that criteria catch all just global minimum.
Yeah, I see what you mean. Yeah, I think, yeah, I understand you.
Just
Mm.
Able to the way people I think it would be very well. I stop with this.
Okay, okay.
Another question. I was surprised because as you do every iteration of it, I would have very happy to see a comparison of some results with results of what we can obtain with iteration. For example, your filter, you demonstrate that it's efficient, but it is more efficient than all activity or not, or I don't know. What can you say about this?
You are talking about literature that relates to estimation of boundary conditions.
I was talking about the efficiency of filter what of the filter that already exists and even. For me, for example, if I do a classical, very simple analysis with no filter, with principle performance analysis, for example, filter that are not the Kalman one, but the one, and prove that this one is the best.
And we are trying what problem we are trying to solve? We are trying to estimate the stiffness of the object. We are trying. Yeah. Could you specify what problem we are trying to solve? We're trying.
I just filter that is the information, but if I use the Kalman filter, number one from the better or it's not better. My remark is, can you prove that the use of the Kalman filter are the best filter? Very good introduce the Kalman filter and prove that it's the best answer. And prove me better.
Well, I actually compared several Kalman filters, and I just say that reduced order version is the best one in terms of this Young's modulus and boundary. The other approaches like variation data assimilation, it maybe also would be nice to compare them, but the problem is that in case of variation data assimilation, it won't work. It won't. It's our problem because Kalman filter allows us to continuously update our model, so it's a surgical process when we perform surgery and then we update. Improve the accuracy of our model, while in case of variation data assimilation, we need to get a certain amount of observations, then we need to update our estimation based on these available certain amount of observations. And that takes time, and that, well, while we wait for this estimation, we will lose time, and finally we will update our model much later. So if we compare it with Monte Carlo approach, for example, yeah, the main achievement, the main moment which we're trying to achieve is real-time simulation. So Monte Carlo and will be definitely slower, but well, it might be more accurate. And also, well, what I could also say that, yeah, to compare all these available methods, I also need to implement them, and it will take, because for now I don't know, well, Optimus, I don't know some other plugins like Optimus, which allow us to combine these data simulation approaches with finite element model. And yeah, this will take time.
Question? But for the future, if you were able to have better. Do you think that you will obtain better results?
If we use ligament as
If I can give you the where we are fixed the body, instead of putting a string where you think we will be able to have better results?
So are you asking what will happen if we simulate ligaments as fixed points? Orientation.
Don't fit it. Bring where you want it, just to go. And I say you, if I know that my ligament is fixed to the foot, 5 centimeters, I give you the point. And if you put your string between the point and the lever, you think that it's better with us. Or do you think that
we we're trying to estimate not the parameters of strings. We're trying to estimate not the parameters of strings, but their orientations. Okay. Of course, we need to verify this, but I'm not sure. I guess well, it will give worse results because the ligaments are connected liver to some another surrounding organs, and during surgical simulation we deform liver, and so ligaments are also attached to liver will deform, but all other organs, well, they of course they have a bit deformation, but more or less they stay fixed, and therefore these ligaments are attached liver to some more or less fixed environment. So it would be better to simulate them as maybe not as masking system, as a bit more complex model. But it would be still nice that they fix the liver to some fixed environment. I'm not sure if you understand.
That's my question, I think. It's very easy job. It's very easy to read it. It is to stick with you and that. Forget.
Thank you.
So, a little bit slow. Okay, I'm there. So, Sergei, congratulations with the weight win reading it, and it's impressive. Don't understand every detail of it, but very interested in kind of how this technology can be transferred into the total picture and workflow of what we looked at the Hyphenau project. So Sergei, he was one of the PhDs in the Hyphenau project that then coordinated or coordinated. And I think that both yours and Sergei Nikolaev's work, the INRIA work, was one of the most kind of works that stick most out from the more common ways of looking into navigation and soft tissue navigation that we brought in the biomechanical modeling into that workflow. And that were lightweight models so that it could be working closer to a clinical work. So when it comes to this clinical workflow and the time needed, if you look at it into a practical setting, these different steps that you need to take in order to prepare a certain surgical case and
use it to register to the patient and make it as a improvement of the navigation accuracy and
That was is which I got with a reduced order Kalman filter with preconditioning. It's 17 20 5 approximately 5 frames per second. So it's several times slower, yeah, but I still hope that we use the CPU version, and with GPU version we could improve it.
what do you mean by actually everyone has been asking about this slide number 18. And my question to you was, this mastering system is approximately 30 times faster than what I didn't.
Then the ligament, this hyperelastic finite element model.
There are the other steps in order to kind of prepare this boundary condition if used in a clinical scenario. What is the time needed to set up the model and make it work to have a certain patient that you want to use this?
Oh, so now we haven't verified it on patients, only on human cadaver. We did experiment on the human cadaver, but at least in this approach we're trying to apply an approach which requires minimization of additional, which requires minimal of additional equipment. And so we need to check the camera, we need to maybe I need to rephrase the question. Is how much time it will take to generate a finite element model if we have a CT scan of patient, to initialize boundary conditions, to
more, I mean, some of the steps needed you can take offline, right? Intraoperatively.
Well, interoperatively, we still need to register statistical atlas. I know we could do it on preoperative model, yeah. Okay, then we need just to register the created model on intraoperative data, and depends on what approach we used. The ICP approach, and it works in 20, no, maybe 10-20 seconds on registration. And then yeah, then we have already a liver model which is in ideal scenario, which is simulating the behavior of the real organ in real time.
This contribution that you, Jean-Nicolas, and Andrea had on the virtual physiological human, there the accuracy was not satisfying because I think that you hadn't considered the boundary conditions at that time. That it was still something to work on.
Yes.
I think you were talking about that should be kind of finished, and it's in a way back to this questions I told Matthias and maybe especially Gregory had about kind of first of all this method that you described here to the experiment that you did in that work together at the end of the Hypernappa.
We could what we could do is we could register these boundary conditions on the preoperative model, then create this masking system, and then try to deform this preoperative model together with boundary conditions model. and it might give us more accurate result.
That would be interesting to see, because that would kind of, in a way, validate somewhat what you have done here, right?
Well, a certain part of the work, yeah, yes,
Yeah.
but only maybe the construction step, because for correction step we need interoperative data, and we need to, because the boundary conditions are correct based on interoperative data.
Yeah. I'm thinking more. No, that was back to this. When it comes to this ligament and the boundary conditions, how? Because you have said it, but how did you find boundary, or where to construct the boundary conditions? How do you define where on the liver you wanted to kind of define the boundary conditions?
Based on statistical atlas. So we have 15 models with segmented ligaments. We construct a statistical atlas from that, and then we register this average shape with statistics on our target shape. And we, as initial approximation of our ligament positions, we use this statistical average. And then we selected a set of models. We exclude a set of vertices. We exclude them along mesh normals and generate spring system. It's only approximation in positions and in springs orientation, but for now it's the best we could propose to generate this mass spring system.
Do you think it would make any difference if you define some? I mean, some parts of the liver are quite fixed. For example, around where the liver is attached to the vena cava inferior. Okay, they don't do much.
Yes, but in the last validation experiment, I also fixed those parts which are related to blood vessel system.
And how was, yeah, so that is already done, and then you have this spring mass.
Well, I simulated them as fixed region, but I'm still thinking that maybe we have to also to use a more complex model for blood vessel system and also simulate them as some deformable model, which describes the behavior of smooth muscles, from which the blood vessels are composed of.
In your opinion, what is the most challenging part now to kind of tackle in order to make this as a useful tool into a navigation workflow?
The most challenging, as you could see, despite I proposed all those approaches, when I tried on real patient data, there are still there is improvement, but improvement is not so big. And then I think about certain reasons, and when we look at these reasons, there are also a lot of other stuff which we could take into account, especially. I guess the most important stuff is contacts with surrounding organs, which is I could try to do some work on that, and I could try. I actually haven't added this in my thesis, but we try to estimate some contact parameters based on Kalman filtering approach, and for simple objects we could finally found some positions of the contact for simple objects and in simple cases. But the problem is that the liver is surrounded by all these contacts, and we have only a small amount of observations. So I'm not sure if we have such amount of unknowns, we could estimate something reasonable if we estimate both ligaments parameters and contacts. So I guess there are still a lot of work to do to apply it in real clinical study. Oh, well, in real clinics.
Is there anything that you, I mean, it's always interesting to ask at the end of the PhD work, if you knew what you knew or know by now, and you were going to start all over again on your PhD, is it anything that you would have done different?
In my process, I guess, well, I'm still thinking that what was proposed here is maybe not the best, but one of the best approaches with respect to the data that we have. So, still Kalman filter, this large deformation metric mapping. On the other hand, if I know what I knew, maybe yeah, I could definitely look at this finite element model more carefully and try to validate how they behave with if they behave according to stress strain curve. And it would be maybe also nice to do the experiment on a real patient much more earlier to see what problems we have and how we could yeah, in case of experiment with a real patient, I actually also wanted to do an elastography measurement of stress strain curves, and maybe we could also try to track the surgical instruments with an external tracker and try to simulate the impact of those tools. But unfortunately, because of these COVID times, we could perform experiment only like we performed it, without all this additional equipment. But it will be nice to apply all possibilities and all what we know to get much more knowledge related to this real patient experiment, and to see how will this knowledge will help us to estimate not boundary conditions, but this knowledge will help us to improve the model, the accuracy of our liver model.
That was my last question. Thank you very much for impressive work with a very challenging task. And it has been a really important contribution for the HACNA project. And we look forward to see what we can do with this, what you have done there, and how it can be used in a clinical scenario. Thank you very much, and congratulations.
Thank you, Ole. Well, the Near-Hookean model is described by Young's modulus and Poisson ratio. Okay. maybe, but well, I usually like Sentinel Kirchhoff material. I usually looked at Neohukin material as a material that characterized by two parameters. And, and right. But okay, the other one is Poisson ratio.
And in your team, you try to
Uh, but yeah, I see. I have an idea that it's better to have not very accurate model but still in real time than to have more accurate model but not in real time, because when you have not accurate model but still in real time, you could see still follow what is happening in area. And well, when we could talk about streaming, sometimes if its stream is not very accurate but in real time, we could still follow it. If it's accurate but not in real time, we're not following it anymore. In case of model, when it's not in real time, what's happening on augmented reality system is not corresponding to what surgeon performed. And well, I saw a nice video on YouTube where, well, it's a science fiction video, but it was about a guy who suddenly stopped interacting with reality in real time and started interacting with a certain delay. And yeah, it was a funny video because he tried to do some stuff and finally it was completely a disaster, because he tried to drink a glass of water, but finally, since it was in a delayed time, the water just flows away. Tried to drive a car, but when he pressed the gas pedal, yeah, he just crashed the wall. So I guess the real time is in this case is at least in the term in augmented reality is more important, because we need to see what happens in real time. But as far as we are there and we have a certain amount of frames per second, we could now then improve the complexity of our model and simulate it more accurately. So that's okay. Yeah. Okay, yeah, yeah. But I use cubic masking system, so it's also hyperlastic behavior. Uh, so it behaves like cubic. Yeah, in case of movement, yeah, the ligament models attached to liver, so with yeah. No, no, no. Okay. Mm. Which learned to from the Kenman teacher. And just to finish, I think on the more personal level, 2 years, never really as appreciated your kindness. Also, really I miss. Thank you, Stefan. Well, I'm not only computer science, I also graduated as a mathematician. And as a mathematician, I like perfectness and try to do some stuff the best possible way. That's why sometimes when things doesn't go well, despite it looks like it's simple to this, I was so frustrated. Thank you. I have to, okay.
review has been identified in your presentation in order to develop. We perform a long session of the question in a wide range of topics. A very interesting the jury not answer. And this highlights the strong expertise you acquire during your question and the maturity of the reflection. In addition, and you have a noticeable knowledge in mechanical physics. Of course, you have shown a good visual understanding. Based on this, the property is ready to achieve gamma output for calculation.
Thank you. Thank you very much. Actually, yeah, for me it also was an interesting journey, which goes for 4 years. Well, in general, PhD is 3 years. So it was the first time when I lived in another country for so long time, and also during my hypernav trips, I have never did so much journey in my life. And this hypernav training event, second event. Thank you very much for this nice journey, for the providing me with money, with a lot of advices, with corrections that you do in my thesis, in my speech, not during thesis defense, but during mid-thesis defense and during some repetitions. Well, I dedicated this work to my parents. Thank you very much. Thank you all.
Thank you very much for the outside.
We'll drink more for you. Thank you again, Gregory and Matthias, for reviewing the manuscript during your summer vacation. I understand maybe the time. Thank you, Jakob, for being with us for the second time.
Thank you.